Alright, homies, today we're talking about glomerular filtration rate, or, because I'm going to get tired of saying it and trip over my words, GFR. Boom, you can read that. Okay, so glomerular filtration rate refers to the amount of filtrate formed in all the renal corpuscles of both kidneys per minute. So for an adult male, the average is 125 milliliters per minute. Now, it's really important that you maintain a proper GFR for homeostasis. So if GFR is too high GFR, that means that there's more stuff being filtered per minute. All the filtrate formed. So more filtrate formed per minute than there needs to be. And that means that a lot of important substances are not being reabsorbed because it's going through so fast. It's just so much of it. So the nutrients that we need that are usually reabsorbed in tubular reabsorption are not reabsorbed. So you lose vital nutrients in urine. Now, if it's too low, that means you're not forming enough filtrate per minute. And that means that waste products that you really want to get rid of and excess hydrogens that could cause like your blood pH to go down, those are not getting excreted. So you're holding on to waste products, and that can be bad for obvious reasons. Now, there are three main mechanisms that control GFR. Let me just erase those. I'm getting an arm workout right now. Alrighty, so three main mechanisms that control GFR. FR, you probably can't read this, but the first one is renal autoregulation. Renal autoregulation. You can't see that. Okay, so this is two components. So we have myogenic mechanism and tubuloglomerular feedback. And then second, we have neural regulation. And then finally, we have hormonal control. Specifically through the Renin-Angiotensin-Aldosterone pathway, or the RAA pathway. Alrighty, so the first step, autoregulation. These are mechanisms that maintain a constant GFR despite changes in the arterial blood pressure. So the first one, myogenic mechanism. So the system senses that there's a rise in BP. Throughout the body, there's a rise in blood pressure. Now, that is reflected even in here, in the kidneys. If it's systemic, think everywhere. So we have a systemic raised blood pressure, and so that stretches the afferent arterial. So let me that's probably not going to erase because these are water-soluble markers, or at least some of them are. So it's going to stretch that. Now we don't want that because that is letting too much water flow into here, and that's going to make it go out too fast. So we have smooth muscle inside the arterioles that are going to contract, reducing the GFR to its previous level in seconds. So let me use black. So we have smooth muscle that kind of contracts there and turns it back to its normal size, reducing GFR. Conversely, when we have a low systemic BP, the smooth muscle in the afferent arteriole relaxes, allowing more blood to go through and thus be filtered into the filtrate, raising GFR. Tenses. Alrighty. Now, tubular glomerular feedback. So part of this is important to know the juxtaglomerular, juxtaglomerular apparatus. So that is when the afferent arteriole is kind of like down here, and you have these special little cells in there called, I believe, juxtamedullary cells. Let me double check that. No, juxtaglomerular cells. Alright, so we have juxtaglomerular cells, and these are smooth muscle cells. Now we also have cells in here called the macula densa. So, when we have elevated systemic BP, this raises the GFR, because remember, more blood's flowing into the glomerulus and thus being turned into filtrate and excreted. So, the macula densa detects, it's kind of an osmoreceptor. It detects certain substances in the GFR. So when GFR is too high, remember, not enough crucial substances are being reabsorbed. So the macula densa over here detects the high sodium, high chloride, and high water that aren't being reabsorbed properly. So the macula densa detects these, and it secretes ATP. So the ATP is metabolized by the mesangial cells. I'm not entirely sure what those are. Just bear with me. To create adenosine. Adenosine is a vasoconstrictor. It vasoconstricts, making that smooth muscle do its thing, vasoconstricts the afferent arteriole, which stops as much blood from heading through and getting into the glomerular capsule. It also inhibits the release of nitric oxide, and this is a vasodilator from the juxtaglomerular apparatus. So right here is the juxtaglomerular apparatus. It's kind of when these two touch, the afferent arteriole and the distal convoluted tubule. It's when those touch, and they're connected by some connective tissue. So it inhibits the release of nitric oxide, a vasodilator, from the juxtaglomerular apparatus, which results in vasoconstriction of the afferent arteriole. So we get double vasoconstriction, causing a lower GFR. And that keeps GFR back in within homeostatic ranges. Now, neural regulation. If you remember, that was kind of a loud thump. Blood vessels of the kidney are supplied by sympathetic fibers. Sympathetic. So, these control the diameter of the blood vessels. So at rest, the afferent and efferent arterioles are maximally dilated because there is no sympathetic activity or minimal sympathetic activity. So they're maximally dilated, fun stuff. Alrighty, so under extreme stress or blood loss, sympathetic stimulation constricts both the afferent and efferent arterioles, the afferent to a greater degree. So we'll just kind of do that, which means there's more pressure over here, stopping as much blood flow from going, and then also the pressure over here makes sure that the GFR is decreased, because the higher pressure, lower pressure. Alrighty, so this shunts blood flow to other vital organs because you want to hold on to as much water as possible during these times. And this overrides autoregulation and that stuff. Alrighty, now, hormonal regulation. Let me just clean up our smooth muscle. Contraction, whatever. Constriction, that's the word. I got it right. Alrighty. Guys, don't hate, I'm in high school. Alrighty. So, the hormonal regulation. This is the Renin-Angiotensin-Aldosterone pathway, or RAA for short. So, there is some stimulus that causes a decrease in blood pressure. So, we got a decrease in blood pressure, and the juxtaglomerular cells over here, they're inside the afferent arteriole, so they can understand. They're like baroreceptors. They can sense that the pressure is lower. It's also important to note that with the decreased blood pressure, there's a lower GFR, so we're going to get lower concentrations of Na+, Cl-, and H2O. And that kind of talks to the juxtaglomerular cells through this connective tissue that connects the afferent arteriole and the distal convoluted tubule. I don't know if you can see that any better with me out of the way with my big head. Alrighty, so the juxtaglomerular cells secrete the enzyme renin. So the enzyme renin goes through the blood, blah, blah, blah. Now, in the blood, renin kind of goes past. That's an awful liver. And it's worse because it's mirrored. Okay, anyways. So the liver secretes something called angiotensin 1. And so this is not anatomically correct whatsoever, but we have renin moseying its way through. Sorry, I messed up here. The liver secretes angiotensinogen. Angiotensinogen. And so the renin meets up with the angiotensinogen, and that kind of cuts off that ogen, and that forms angiotensin 1. Angiotensin 1, or A1. Now, that A1 travels through the bloodstream, where it meets the lungs. Inside the lungs, there's this enzyme called ACE, angiotensin converting enzyme. So when A1, here we'll kind of, again, this is not anatomically correct whatsoever. When these two combine, the ACE turns the angiotensin 1 into angiotensin 2. Now, angiotensin 2 is the big deal that we want to talk about. Angiotensin 2 has several functions. So first of all, angiotensin 2 is a vasoconstrictor. It vasoconstricts the efferent, and to a lesser degree, the afferent, to maintain GFR despite the low blood pressure. So if we have low blood pressure, how does this work? That's a good question. I will get back to you. Okay, your girl was being a little silly. I remember now. So, remember, we're dealing with a low BP, and that results in a low GFR. So we want to maintain GFR so that we don't end up with waste products and stuff. We want to make sure that we're getting enough of our nutrients reabsorbed or excreted. So low GFR. So the first thing angiotensin 2 does is it constricts the efferent arteriole, and to a lesser degree the afferent. That's not really important. We don't really need to bother with that. But in any case, this vasoconstriction keeps more blood pooled up in the glomerulus so that it goes into the glomerular capsule. So with more blood going into the glomerular capsule, it's increasing GFR. So we get GFR because we're getting more blood turning into filtrate, going through, reabsorbed, etc., secreted, whatever we need. Second, angiotensin 2 acts on the adrenal cortex to secrete aldosterone. Aldosterone, so I'm just going to put that right there. Aldosterone increases Na plus reabsorption. And that obviously, remember, salt sucks, Na plus. So we have Na plus going from the filtrate, more from the filtrate into the blood. And so water is following because salt sucks. Water goes where sodium goes. Now, because of that, if you remember, so we're going to have more water in the blood vessels, and that's going to increase blood volume, which thus in turn increases systemic BP. So we get increased BP. Now, what it also does is angiotensin II acts on the third center up in the hypothalamus to increase water intake. So it makes you drink more H2O. Lastly, it also acts on the posterior posterior pituitary, I'm losing my mind, causing increased water reabsorption. So, antidiuretic hormone, increased ADH. Think about it, ADH, antidiuretic, that means you pee less. And antidiuretic hormone causes increased permeability in the collecting duct, so that more water goes out of the collecting duct into the blood vessels, thus increasing blood volume and thus increasing BP. So that is how angiotensin II works and the hormonal regulation works. So that is all three mechanisms that help control GFR and maintain it. And yeah, that's about it.